Alright, so what you see is a cart that's just oscillating back and forth. Now the question I have is this considered harmonic motion? So what does harmonic mean? Don't know, right? What's harmonic? Anybody know the word harmony?
Is the amplitude
What's harmony? What's harmony?
In unison.
In unison. Yeah.
Is a wave.
Simple harmonic. Harmonic motion. That means motion that goes back and forth. Back and forth and back and forth. And it's always kind of the same, and it repeats. If something is in simple harmonic motion, what does that mean? Simple harmonic instead of complex harmonic motion. There's no forces acting on
No,
it.
I said no new forces.
New forces. Oh, really?
instead of like going up and down and around, it just goes back.
Well, could you make this mass go in complex harmonic motion?
Yeah, sure.
Sure, watch.
So just not.
This is no longer simple. This is considered complex. Also, complex might be something like this. What was your...
Smooth curve.
What kind of curve?
It goes constantly around.
What kind of curve? What kind of
Sine
curves?
curve.
Sine curves. That's what we talked all about yesterday, right? We talked about sine curves yesterday. And the reason we talked about that is sine curves are simple harmonic motion. Now, what is the easiest way to get not simple harmonic motion?
Hold it. Make it digital. Add a new force.
Wait, I thought sine curves started
During its thing.
Sine cosine, rather sinusoidal curves. Sine and cosine fall under the category of sinusoidal, right? So, sinusoidal motion is considered simple harmonic motion. All right, so in order to get sinusoidal motion or simple harmonic motion, what's required?
a returning force to make it.
Haha! Yes! Think about this. If I pull the cart in the positive direction, what direction is the spring going to push it? Back negative. Does that make sense?
Yeah.
So, in order to have harmonic motion, you have to have what's called a restoring force. Right? A force that does what? Restores it to the original. Well, it tries to get it back to the zero position. What if I pull it to the left? What way is the force?
To the right.
To the right. So if you pull to the right, the force is to the left. If you pull to the left, the force is to the right, and so on. So you have to have a restoring force. Now, also, in order to get harmonic motion, there's one other requirement. Something that this has to have, or else... the mass doesn't need to be constant, but it does have to have mass. Right? Think about this. If this were massless, and you pulled it this way, there's going to be you pulled it to the left, there's going to be a restoring force to the right, right?
Yeah.
What would happen when it got to the middle?
Stop.
It would stop. Why do you need to have inertia? To keep it going past that middle point on to this point, right? So two requirements for harmonic motion. You have to have a restoring force to pull it back to the zero spot, and then you also have to have inertia to keep it going past the zero spot. Does that make sense? Now, let's say that again. Sound, simple harmonic motion. Okay, so what is sound? A pressure wave, right?
Yeah.
A pressure wave. Now, do you guys know the difference between a wave and an oscillation? This is not something that is really part of this class, but actually it kind of is part of this class. What's the difference between the word wave and the word oscillation? Are they the same thing?
Yeah. Okay.
Yeah, there's one that's like straight through.
Yeah, because
Is this a wave or is this an oscillation? This particle is oscillating. Good. What's the difference between that and a wave?
Oh, waves.
Oh, waves keep going. The oscillation goes back and forth.
Ah, you're missing the big picture. A wave is what happens when you have a bunch of particles and you start one of them oscillating. Right? Let's say we had a slinky. And that slinky is made up of particles called atoms, right? You take one of those particles and you pull it in a transverse direction and then push it back again. You're taking that particle and oscillating that individual particle, right? What does it do to the particle next to it? Causes it to oscillate. What does that do to the particle next to it? Causes it to oscillate. The one next to that causes it to oscillate, and it to oscillate, and then it to oscillate, and it to oscillate, and then it to oscillate. So what's the relationship between oscillations and waves? Oscillations are what individual particles do. It is the movement taken by an individual particle. If you have a string of particles and you start one of them oscillating back and forth, the energy from that oscillating will be transferred to the next particle, causing it to oscillate. To the next particle, causing it to oscillate. To the next particle, causing it to oscillate. And that movement of energy is called a wave. Does that make sense? So is this a wave? No, it's not. So what about light?
Well, that takes on both properties of still massless.
Ah, you're saying, so light is a wave that doesn't involve any particles. Is he correct?
It travels because it goes through.
Doesn't light?
Wait. Let's answer that light question.
Isn't light?
Light has mass.
Okay, so in the modern physics interpretation, light is a particle. But in the classical physics interpretation, which is all that we're going to talk about, light is a wave, right? Is a wave that doesn't require any particles in the classical interpretation, right? So what is the thing that's oscillating? And by the way, we are way ahead of ourselves right now.
Yeah, it's the frequency that's oscillating. Like
The frequency,
it's the wave properties of light.
the wave is the wave that's oscillating? What is the thing that's oscillating?
The photon.
We
No.
don't know about photons. Do we know about photons?
No, that's a modern physics thing. We're not allowed to talk about that in this class. The nothing, exactly. And specifically, when we talk about nothing, we are called, by nothing, I'm assuming you're referring to the electric field, right?
Yeah.
Right, that. The electric field is oscillating. An electric field does not require a particle to exist in that location. You can have electric fields in free space, in empty space, in a vacuum. All right? And that's why electromagnetic radiation is special in that way, unlike sound, which requires actual physical objects to be shaking back and forth. Those objects we call molecules. Right? Okay, so back to this. We are not talking about waves. Waves are not part of this unit. We are, however, talking about oscillations. In particular, we're talking about simple harmonic oscillations. Now, what are the two requirements for simple harmonic oscillation?
Must have inertia.
Inertia and And a restoring force. Inertia and a restoring force. Inertia and a restoring force. These are the two requirements. So, what would happen if we added more inertia? The amplitude would become larger.
Nothing.
No.
What?
No.
Maybe I'm crazy.
Wait, if I pull this back 10 centimeters and I put some masses, all of a sudden it's going to teleport to 20 centimeters?
Never mind.
Oh.
It's going to lose amplitude faster because of friction forces.
Yeah.
No. Forget about friction.
Nothing.
Oh, are we pretending this?
Is there going to be any difference between less mass and more, less inertia and more inertia?
No.
Watch.
Wait.
Energy slower.
It's slower. Why?
Oh,
It's harder to move
mass.
it.
It's,
more
it's not that it's harder to move, it's harder to
start
accelerate. Means for a given amount of force, it's going to accelerate less. And if it accelerates less, that means it's going to be going slower. Does it change the amplitude?
No.
No, because I control the amplitude, right? By how far I pull it back, right? But I can pull it however far back I want, right? I control the amplitude with the initial conditions. What the mass, what the inertia affects is the speed. Good? Because if I take these out and let it go, it's faster. Yeah.
If those springs had to work
Ha! Okay, so, oh, actually, you went in a different direction than I want. In order to get simple harmonic motion, Macy's question is, what if these two springs are different? One's got a K of like 10 and the other's got a K of like 20 or whatever.
Yeah.
Does that mean it's no longer in simple harmonic motion? The answer is it is still in simple harmonic motion the way I have it set up. You really have to do some funky things with springs, like put them in series. Well, no, even in series it'll still. Anyway, simple harmonic motion. Let's talk about simple. What makes it simple? What makes simple harmonic motion as opposed to complex? Sine wave, a pure sine wave. Pure sinusoidal wave, meaning sine or cosine, not tangent, right? In order to get this, the restoring force must be linear. What does that mean? Trina, do you know what that means? What a linear force is? Linear restoring force? It only points in one direction? Trina's guess at the word linear was that it only travels in a straight line. That's your... not correct, though. That is good. That would be a geometry definition. The calculus definition of linear is this. A force which depends linearly on the displacement. So, if there is zero displacement, how much force is there?
0.
Okay, if at displacement of 1 centimeter I get a force of 10 newtons, if I move it to 2 centimeters, how many newtons should I get? 20 newtons. If I move it to 3 centimeters, how many newtons should I get? That is what linear restoring force means. In order to have simple harmonic motion, the restoring force must be linear. Have we ever seen an example in this class of a non-linear restoring force? Hint, a nonlinear spring.
Whoa.
Have we ever seen that?
A bow.
A bow! Do you guys remember this?
Yes.
When we did this, the bow, we plotted F versus X, and it wasn't a straight line anymore. Remember how it had some curve to it?
Yep.
That bow, if we set it up in this situation, would be a non-linear restoring force. And the motion, if you hung something from the bow and let it go boing, 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 would not be purely sinusoidal. It would like linger in one spot and then linger in the other, and it wouldn't make a... You guys see how you could do that. Perfect sinusoid looks like that, right? But if you had a sinusoid that went up and then kind of flattened out for a little bit and then came down and then flattened out for a little bit, that would be a non-simple harmonic motion. That would be a complex harmonic motion. Yes?
But then wouldn't that one have different amplitudes on each side of like...
Does it? Let's check. That's why I set these guys up. Okay, so I'm going to go 10 centimeters from this side. This side's at 128. I'm going to go to 138. And I'm going to go 10 centimeters from this side, so 111, so 101. I'm going to pull it just to one side and let go and see if it bashes in and or falls short. Ready? Here we go. Science, pretty much the same. Isn't that interesting? The fact that one spring is slightly stiffer than the other doesn't affect it. Okay? So yeah, assuming both of these springs are linear, that's what you're going to get. So, simple harmonic motion is sinusoidal motion, requires two things. Inertia and spring and a linear restoring force. All right. So, how do you affect the inertia of a spring mass system like this? Add mass or take mass away. If you add mass, what happens to the period? Gets longer. What happens to the speed? Slower. Good. Okay, so we can adjust the period by adjusting the mass of the system. How else can we adjust this period? The period. What else could we do to this system to make it go faster or slower? Change the springs. What if we use stiffer springs? What would happen to the restoring force?
It would increase.
Increase.
Yeah.
It would be faster.
Because if you pull it back the same distance on a
Well, think about it. At the end.
Bigger forces, right?
Yeah.
Means accelerate more. So stiffer springs, if I swap these springs out with stiffer springs or with more springs in series, parallel rather, you could make this thing go like crazy, right? Isn't that cool? So what two things does the period depend on? Inertia and the restoring force, or also known as inertia you affect by mass, and the restoring force you affect by K, spring constant. Does that make sense? Yes! So this is how you make simple harmonic motion. Inertia and a restoring force. How do you make the thing go faster? Two things you could do.
Take away mass.
Less mass or stiffer springs. To make it go slower, more mass, weaker springs. Good? Yes! All right. So here we go. Let's go take some notes. All right, so here's the crazy part. It turns out this inertia and linear restoring force idea is super important. Not only is that a requirement for simple harmonic motion, but it also affects the speed or the frequency or the period of the simple harmonic motion. And not only that, it doesn't just work for spring mass systems. We'll get to this later, all right? But I want you to keep this in the back of your mind for a few days from now. What does the period depend on? What does the period depend on? Inertia and the restoring force. Now, depending on the kind of system you have, it's not always mass and spring constants. Can you have simple harmonic motion in a system that doesn't involve a spring? How? How? A pendulum, right? Isn't that have a restoring force? No spring involved, though. Right? And we're going to see this again and again and again later on, even in circuits. We're going to have currents flowing back and forth. Is there any springs involved in the current in a circuit? No. But somehow you can still get simple harmonic motion with electricity. All right? I want you to keep this in the back of your mind for later. Yeah? It's called alternating current, right?
Yeah.
That's simple harmonic motion, right? Interesting. Okay. Let's move on. Let's talk about, in order to get that linear restoring force for a spring, we say F equals negative kx, right? Why is there a negative sign? Because it's a restoring force. It always points back to the direction it came from. What's the K for? That's the stiffness of the spring, right? And notice, as long as it's a constant and doesn't change, that means it's a linear restoring force. Just K, not K squared or whatever. Does that make sense? All right. Let's see. So how do you store energy in a spring? Well, you guys know how to do this. How do you store energy in a spring?
You pull it back.
You pull it back, right.
Change
So
the
here we go.
displacement.
So the energy stored in the spring, well, that would be the work that you do on the spring stores energy in the spring, right? Now, what's the equation for work? The integral of f dx. Somebody was going to say f d cosine theta, right? Which is right. Well, they're both right. It's just you can't use f times d. Why can't you just use f times d in this case for a spring? Because the force is changing. As you pull it back, the force is getting stronger and stronger and stronger. It's not a constant force. So you can't just multiply f times d, because f is different depending on where you are. All right, so what you have to do instead is use an integral sign. So the work done by the restoring force would be negative work, would be the integral of f dot dx, but f is negative kx. So the integral of kx dx, what's that integral? 1/2 kx squared. Pretty cool, huh? All right. You've done this before. We did this before, right? I know, so it's amazing. So the potential energy stored in the spring is 1/2 kx squared, straight from the integral. All right? Now, of course it's cool.
You know, it's cooler than being cool.
No.
High school.
No.
All right.
Staying in school. All right. All right. Let's say that cart, once you pull it back and let go, that cart, when it gets to the middle, does it have any spring energy left? You pull it back, let go, and in the middle, is there energy stored in the spring still?
No.
No. What kind of energy exists?
Kinetic.
Kinetic. So what happened to all the spring energy you started with?
Zero. Well, it got changed.
It got changed into 1/2 mv squared. So law of conservation of energy says the total energy, the potential energy, plus the kinetic energy is what? Constant, assuming you didn't lose any due to friction or whatever. We're going to talk about friction toward the end of the unit.
Okay.
All right? So the total energy, 1/2 kx squared plus 1/2 mv squared, is constant. Here's what I do not want to see on a test. Soham?
Wow. Called out.
I do not want to see 1/2 kx squared equals 1/2 mv squared. Why not?
Because it doesn't always.
1/2 kx squared equals 1/2 mv squared? They don't equal each other. Except for one really weird point right in the middle of the compression, right?
But until you write at center, 1/2 mv squared equals 1/2. It doesn't.
It doesn't. Because the 1/2 kx squared is 0 at that point. Never, ever, ever write 1/2 kx squared equals 1/2 mv squared. It's okay to write 1/2 kx squared initial equals 1/2 mv squared final. That's okay. How come?
Because they do.
Because that's true. But it's not okay to write 1/2 kx squared initial equals 1/2 mv squared initial, because that's not true. Unless on the weird circumstance that it is. But that would be a special case that you're never going to see. All right? So, at the time when the cart has maximum displacement, x is a, right? At maximum displacement, how fast is the car going? 0. It's not moving at all, right? If you pull it all the way back, how fast is it moving?
0.
So how much kinetic energy does it have right there?
0.
0. So all the total energy is going to be 1/2 kx max squared, or 1/2 ka squared. Then when the car is at the maximum speed in the middle, how much potential energy does it have? 0, right? Because it's 0. So it's at its maximum speed. So at point 2, the energy is entirely kinetic. So its kinetic energy is 1/2 v max mv max squared. So therefore, we can make this statement that 1/2 mv max squared is 1/2 ka squared, which is very different than saying 1/2 mv squared equals 1/2 kx squared. Do you see the difference? The difference is in the subscripts. Does that make sense? All right. Therefore, if you do a little math magic and you cancel out the 1/2s,
Mathemagic, that's clever.
I know. What do you get? You get V max equals what?
Square root.
Square root
Yeah.
of what over what? Square root of what over what? K over m. The speed depends on what? The ratio of what? K over m. The restoring force term divided by the mass. What's that? Because that was the amplitude. A was amplitude. All right, guys, this is super, super important. The speed at which it travels, the maximum speed at which it travels, is square root of K over m. Square root of the restoring force divided by the inertia. Square root of restoring force divided by inertia. Remember that. Right. If you went to 1/4 the mass, what would happen to the speed? Double the speed. If you quadrupled the mass, what would happen to the speed? Half the speed. And we could actually do that back with the spring mass system. Put 4 times as much mass there, you'll see that it's going half the speed. Make sense? All right. So, if Vmax equals omega A from yesterday, that means what's omega mean? Omega is angular velocity. Vmax is omega A. That means omega equals root K over m. Right? So what's period? How long does it take to go one oscillation? T equals 2 pi square root m over k. Raise your hand if you've seen this before.
I probably should have, but I don't remember.
This is one of the equations you had to memorize last year for AP Physics B. 2 pi square root of m over k. Do you guys remember that? That was something that in AP Physics B they said, just memorize this. We're not going to derive it, just memorize it. This is where that comes from. 2 pi root m over k. All right? Memorize that pattern. Square root of k over m for velocity, square root of m over k for period. Good? All right. Now, graphs. These are something that show up a lot on tests. What is this a graph showing? Why is there a blue line and a red line? One's potential and one's kinetic energy. What shape is the potential energy graph? Parabola. Why is the potential energy graph a parabola? What's the potential energy at point 0? 0. And what happens to potential energy as you go farther out? 1/2 kx squared, right? That's why that's a parabola. Now, if total energy is a constant, what should the kinetic energy graph be? 1 minus that, which is an upside down parabola, right? So when's kinetic energy at maximum? 0. When's kinetic energy at 0? At maximum amplitude. Now, some people in this room have a habit of saying that 1/2 mv squared equals 1/2 kx squared. Is that ever true? Of course it's true. At 2 points. What 2 points is it true? Here
Between the middle
and there. Those are the only true 2 points when it's okay to write 1/2 kx squared equals 1/2 mv squared. Other than that, they are not equal. Got it? All right. All right, good.
Was that on the test?
Oh, that's been on just about every energy test you've ever taken. And I'm sure half of you, the people in this room are guilty of writing 1/2 kx squared equals 1/2 mv squared.
You did on every test, that's why.
Yeah.
I never did it.
All right, so it's only true at 2 points. All right, that's it. So important stuff to know is this square root of k over m or square root of m over k thing. That's going to show up in a big way a whole bunch of times. All right, that's it.